All right, in this video we're going to look at indeterminate products. And those are ones where when we look at the limit as x approaches a of the product of two functions, one of them goes to 0 and the other one goes to infinity. Okay, when you have this situation, that's called an indeterminate product, and you need to do something in order to get an indeterminate quotient. Let's see if I can fit that on there. So that you can apply L'Hopital's rule. Okay? So, although we're tempted to take the derivative because it seems to make our life easier over here, we can't do that when we have this product. We need to do something first to get it to a quotient, so then you can apply L'Hopital's rule. Now notice that if f of x goes to 0, then the limit as x approaches a of 1 over f of x goes to infinity. Okay? Which means if I rewrite this, the limit as x approaches a of the product of g of x over 1 over f of x, and maybe you need to pause and look at that for a minute, but g over 1 over f of x is the same thing as f times g, right? 1 over f is just f. Okay? Now, if I rewrite it this way, I see the top goes to infinity still, and now the bottom goes to infinity. And so we have an indeterminate quotient. I could have moved the g to the bottom, and notice that if g goes to infinity as x goes to a, then 1 over g of x goes to 0, right? If the top goes to 1 and the bottom goes to infinity, then 1 over that goes to 0. So we could write our original limit as the limit as x goes to a of f of x over 1 over g of x. Okay, because 1 over g is just g. Top goes to 0 and now the bottom goes to 0. And so we have an indeterminate quotient in this form. And in both of those cases, we can apply L'Hopital's rule, but not beforehand. All right? Now, which one we move to the bottom depends on the problem that we have. And you'll get a sense of it the more you practice. All right, let's look at this first example. So here, this is the limit as x goes to infinity of 1 over x times ln of x. And we see that 1 over x as x goes to infinity goes towards 0, and the natural log of x as x goes to infinity goes to infinity. So this is an indeterminate quotient. Now this one's actually kind of an easy one because I see really easily how I can turn this into a, this was an indeterminate product. I can see really quickly, let's write that down, which means we're not ready to apply L'Hopital's rule. We have to do work to get it into a quotient. So notice this is the same thing as the limit as x goes to infinity of the natural log of x over x, right? 1 over x can be written as, 1 over x times ln of x can be written as ln of x over x. Now I see top still goes to infinity, and this time the bottom goes to infinity. So now I have an indeterminate quotient, which means I'm ready to apply L'Hopital's rule. So this is equal to the limit as x goes to infinity of 1 over x over 1. And that's equal to the limit as x goes to infinity of just 1 over x. The top blows up, the bottom goes to 1, this whole thing goes to 0. So here's an example where we took a product and we turned it into a quotient. Then we applied L'Hopital's rule, and we got our answer. All right, let's look at one more example. All right, here we see that, here's another product. 2 times x e to the 2x. We see that this function right here, as x goes to negative infinity, goes to negative infinity. And e to the 2x has a graph similar to this, and as x goes to negative infinity, this thing goes to 0. Okay, so now we have an indeterminate product, and we need to do some more work. Now, I can move one or the other to the bottom. It is tempting to move the 2 to the x to the bottom. Okay, so we may have 2 to the x over 1 over 2x. I'm going to write over here in red a common error when people are first looking at indeterminate products, and that's just to move something to the bottom. And remember, if I have 2x on the top, just moving it to the bottom is actually wrong, right? It's not 2 to the x is not the same thing as 1 over 2 to the x. 2 to the x is the same thing as 1 over 2 to the x. So don't do that. Okay, now if we go this route, well, first of all, we see this is 0, and this is also 0, so now we know we have an indeterminate quotient, and so we are ready to apply L'Hopital's rule. And so we get the limit as x goes to negative infinity of 2e to the 2x, and then this one becomes negative 1 over 2x squared. All right, now look, the top still goes to 0 and the bottom still goes to 0, but this isn't getting better. And if I were to do this again, I'm still going to get an e to the 2x on the top, and my power is only going to get higher. Okay, so this path right here was probably not the one we wanted to do. It wasn't incorrect, it just didn't work for us. So we are going to scratch it off, and we're going to start again. And so this time I'm going to move the e to the 2x to the bottom. Okay, so this limit, our original limit, is equal to the limit as x goes to negative infinity of 2x over e to the minus 2x. You might need to pause and look at that to make sure you believe that. But 1 over e to the minus 2x just is e to the 2x. Okay? Now we see the top goes to infinity. And remember my graph of let's rewrite that. That's an e to the 2x, so e to the minus 2x looks like this, right? So as x goes to negative infinity, e to the minus 2x goes to infinity. Whew! That's a good thing, because otherwise we would not be an indeterminate quotient. Okay, but it is an indeterminate quotient, so we're ready to proceed. So let's look at the limit. As x goes to negative infinity, the top becomes 2, and the bottom becomes minus 2 e to the minus 2x. I see my 2's cancel, and I'm left with the limit as x goes to negative infinity of minus 1 over e to the minus 2x. We know that as x goes to negative infinity, e to the minus 2x goes to infinity. The top goes to negative 1. This whole thing goes to 0. Okay? Now go practice.